Hi, this is the Science Chef. In this video, we'll be answering the qualitative analysis questions of the 2016 WAEC Alternative to Practical Chemistry in preparation for the 2023 WAEC GCE. Alright, let's start. Question 2. D is a simple salt. The following tests were carried out on D. Copy and complete the table. Test. D was heated strongly in a hard test tube. Observation. Colorless gas with pungent or irritating smell evolved. Gas turned moist blue litmus paper red. Black residue was left. Alright, let's analyze this question. First off, what are things to note here? D is a simple salt. For the fact that it is a simple salt, it means that it contains one cation and one anion. So, the following tests were carried out on D. Copy and complete the table. D was heated strongly in a test tube. Whenever a substance is heated, what is being tested for is the thermal stability. And in my previous video, I told you that there are actually three major categories of compounds whose thermal stability can be tested on. That is the trioxosulphate 5, NO3-, the trioxocarbonate 4, CO3 2-, and the ammonium ions. Right. And whenever you are testing for a thermal stability of a compound, if the compound is not stable to heat, if it decomposes on heating, it will likely produce a gas. But if this compound is stable to heat, it will not decompose, there will be no reaction. So in this case, in these three compounds, I told you that the gases that will be produced when any of these compounds is heated would be NO2 gas for the trioxosulphate 5, the CO2 gas for the trioxocarbonate 4, and ammonia gas for the ammonium compounds, right? And I also gave you how to identify these gases if they are eventually given off, right? I said this one is has a reddish brown color. This is a colored gas, reddish brown, and it's acidic, and it has a pungent smell. For CO2 gas, I said this one is a colorless gas. It's also acidic, but it's also odorless. So it's odorless, colorless, or odorless. But it's an acidic gas. While this one is also a colorless gas, it's acidic. In other words, it turns blue litmus paper red, but it's not an odorless gas. It has a pungent or choking smell. Pungent, choking, or irritating smell. Good. Now, based on this, to be able to identify any gas that is given up, you can use it as a preliminary test to identify the gases. Sorry, ammonia is not acidic. Ammonia is alkaline. Ammonia is alkaline because it turns red litmus paper blue. But if you want to confirm the presence of the gases like CO2, you may need to use lime water to confirm it, right? And of course, that will also tell you that CO3 2- is present. For NO2 gas, you may need to carry out the brown ring test using freshly prepared FeSO4 and concentrated H2SO4. That will give you a brown ring in the test tube. So that confirms the presence of NO3-. While for ammonia gas, yes, ammonia gas, in a way, this can confirm that it's ammonia gas because of its one, unique smell, and two, it's the only commonly used gas that is alkaline in nature, right? Those may still need to carry out further reactions by reacting the compound with sodium hydroxide and warming it. That's just by the way. But the challenge here in this question is that the gas evolved does not fit into any of this. Look at this. It's a colorless gas with pungent or irritating smell evolved. Now, the two colorless gases that we have here are CO2 and ammonia, right? And CO2 is odorless, doesn't have a pungent smell, so it cannot be CO2. And ammonia has a pungent smell, good. But we are told that the gas turned moist blue litmus paper red, telling us that the gas is acidic and not alkaline. So it cannot be ammonia because ammonia is alkaline. If it were to be ammonia, that reaction would have been gas turned moist red litmus paper blue. Are we together? So it means that there's another group of compound that is being tested for, which we did not mention in our last tutorial, and that is SO3 2-. That's the trioxosulphate 4. Now, if you heat this class of compounds, the trioxosulphate 4, they will decompose to give you SO2. Generally, they will decompose to liberate SO2, and SO2 is a colorless gas that is also acidic. I told you why they are acidic. First of all, they are acidic oxides, they dissolve in water to form acid water solutions, or they react with bases or alkalis to form what? Salt. The gas is colorless, acidic, and has what? A pungent or irritating what? Smell. Actually, SO2 has a unique smell like that of a burnt matches. So you can easily use that to identify SO2, right? So with this, it is obvious that the gas would be what? SO2. Are we together? So since we have only two provisions here, probably we're not asked to write the inference for the gas involved here. But if I were to write these exams, I would still write it. I just write the inference for a colorless gas with a pungent or irritating what? Smell. But since we are not asked, there's no provision for that. Let's leave it. Let's come to this gas turn moist blue litmus paper red. Here, the action or the effect of the gas on litmus paper is being tested here, right? So obviously, it means that the gas is what? Gas is acidic. An acidic gas is evolved, right? Then there's something here, a black residue was left. Now this also brings us to ammonium ions, so ammonium compounds. Ammonium compounds that produce ammonia gas when heated do not always form residues. Yes. So because of this black residue that was left, and also the acidic nature of the gas, definitely can confirm that it is not what? Ammonia gas. Are we together? So in your syllabus, only one solid will give us a black residue. Let's try to write the chemistry. The chemistry here is that when you heat this guy, it decomposes to give us what? SO2. But we are now told that there's another substance left here, which probably is what? An oxide. Are we together? Which oxide, based on your syllabus, is black? Now, based on your syllabus, the commonly tested oxides, solid oxides, are, or metallic oxide, you call it that way, based on your syllabus, right, are zinc oxide, lead 2 oxide, copper 2 oxide, and probably calcium oxide. Right? We told you in the last tutorial that zinc oxide is yellow when hot and white when cold, while lead 2 oxide is reddish brown when hot and yellow when cold. While copper 2 oxide does not change color, it has only one color. But before we come to copper 2 oxide, calcium oxide also has one color, it does not change color. This one is always what? White. While copper 2 oxide is always what? Black, whether hot or cold. So the black residue that was left could be copper 2 oxide. We are not sure, so let's just write that residue could be copper 2 oxide. That's CuO, right? Residue could be copper 2 oxide. Fine. Let's move on to the next question. We are told that D plus distilled water and stirred did not dissolve. No, when D was added to distilled water, it did not dissolve, right? Which makes sense. From what we have done so far, you could easily tell that that gas or that salt is actually CuSO3. Yes, it contains Cu2 plus and SO3 minus. And most trioxosulphate 4 salts are insoluble in water, apart from potassium and sodium, or the group 1 word trioxosulphate 4. So this makes sense a bit. Now, why am I saying copper 2 plus? Because of the copper 2 oxide, because of the residue that was formed. For that copper 2 oxide to be formed means that the salt itself is a copper 2 salt, right? And from the suspicion of the gas that has been released, it's as if the anionic radical present in that salt is SO3 minus. So let's continue. We don't know. I'm just suspecting. So now, since it did not dissolve, it means that D is an insoluble salt. Since D did not dissolve in water, it means that D is an insoluble salt. The next test now, D plus dilute HCl. Remember, these trioxosulphate 4 salts always tend to behave like the trioxocarbonate 4 salts, right? Trioxocarbonate 4 salts, when trioxocarbonate 4 salts are heated, they produce what? CO2 gas and O2 minus. That's an oxide, corresponding oxide. But when SO3 minus salt is heated, it produces what? Or they produce SO2 gas. SO2 gas and what? And the corresponding what? Oxide, right? Now, remember when the trioxocarbonate 4 is reacted with an acid, CO3 2- plus acid, what happens? CO2 gas and a salt is always what? Formed, right? In other words, CO2 gas is always what? Liberated. Similarly, when SO3 2- is reacted with an acid, SO2 gas, a salt, and water is also what? Formed. In other words, SO2 gas will be what? Liberated. So now, that is the chemistry of this reaction here. I told you that the preliminary test up there gives us an idea of what the ion is. That's SO3 2-. Now, this D plus ACl is now telling us more about the ion. Now, that ion, the ion present in the salt, produces a colorless gas with pungent or irritating what? Smell. They're now repeating that observation that we had in the first test when we heated it, right? They now went further to test the gas with acidified KMnO4. And what happened? Gas turned acidified KMnO4 solution colorless. Look at this now. A colorless gas, pungent irritating smell, right? Now, a gas that turned acidified KMnO4 colorless can only be a reducing agent, because acidified KMnO4 is an oxidizing agent, right? So, which of the gases in a qualitative analysis syllabus are reducing agents? Now, the two gases commonly used as reducing agent in qualitative analysis are SO2 and hydrogen sulfide. SO2, that's sulfur 4 oxide, right? And hydrogen sulfide. Hydrogen sulfide is a major reducing agent. It always acts as a reducing agent. But sulfur 4 oxide can either act as a reducing agent or an oxidizing agent, depending on what it's reacting with. In the presence of a strong reducing agent like a hydrogen sulfide, it will act as an oxidizing agent. But in the presence of a strong or stronger oxidizing agent like acidified KMnO4, it will act as a reducing what? Agent. So in this case now, how do we know that this gas is not hydrogen sulfide? Remember, hydrogen sulfide is also what? Colorless. It also has a pungent or irritating what? Smell. But the problem is that sulfide salts do not decompose on heating. So that's why I did not add sulfides as a preliminary inference in my first analysis or in the first test. But here now, hydrogen sulfide can also react with acidified KMnO4 and it will turn it colorless. That's from purple to colorless. How can we know that the gas is not hydrogen sulfide but sulfur 4 oxide? The difference in the reaction between these two gases and acidified KMnO4 solution is that the reaction with hydrogen sulfide produces yellow precipitates or deposits of sulfur. The acidified KMnO4 will always oxidize hydrogen sulfide gas to sulfur. In other words, the hydrogen sulfide will change from S2- to S0, which is solid. And that will be seen as yellow deposits of what? Sulfur in the reaction vessel. But since we were not told that there was any yellow deposit or there were any deposits of sulfur, it means that it cannot be hydrogen sulfide. On the other hand, acidified KMnO4 oxidizes sulfur 4 oxide to SO4 2-. So that's to tetrioxosulphate what? 6. In other words, we have something like SO2 will be oxidized to SO4 2-. That's from +4 to +6, right? And there will be no deposit, no yellow deposit. So when once that happens, it means that that gas is obviously sulfur 4 oxide. Are we together? So now, what are they testing for here? Gas turned acidified KMnO4 solution colorless. So what does that mean? It means that gas is a reducing agent, right? For it to decolorize acidified KMnO4 as a reducing agent, then which gas can do that without yellow deposits? The SO2 gas evolved. So which ions will produce SO2 gas in a reaction? That will be SO3 2- present, or you can say confirmed. This test is a confirmatory word test for SO3 2- using acidified KMnO4 solution. SO3 2- is a reducing what? Agent. but CO3 2 minus is a non-reducing agent. Are we together? Now note that SO2 gas can also form a milky precipitate with lime water. Yes, just like CO2. But the only thing that you would use to distinguish them is one, the odor and the reaction with acidified KMnO4. If the gas is SO2, it will have the odor of burnt matches, which is pungent or irritating. Then it will turn acidified KMnO4 colorless, while CO2 gas will not. Are we together? So at times it's not always enough to use lime water alone to confirm the presence of CO3 2 minus. Are we together? You need that knowledge maybe for your question 3 or even for your theory or objective questions. So the next question here says portion of solution from 2B II. Now D had dissolved in dilute HCl, right? So we now have a solution of what? D. So you can now use it to carry out further what test. Portion of solution from 2B2 II plus aqueous sodium hydroxide in drops, then in excess blue gelatinous precipitate insoluble. Now you don't need to waste time here. There are some questions you don't need to waste time on. From that residue, we already know that the salt will contain copper 2, right? And now this test is now trying to confirm to us that copper 2 ion is actually what? Present. So blue gelatinous precipitate, from our syllabus, which ion will give us blue gelatinous precipitate in drops and precipitate insoluble in excess sodium hydroxide? That can only be what? Copper 2 ion. Are we together? So let's not waste our time. So here we have Cu2 plus present. I've told you that you don't write suspected again. You don't accept it. So just write present. Same here, Cu2 plus present. Not confirmed. This is not a confirmatory test for Cu2 plus. It is now the next test that will now confirm the presence of Cu2 plus, right? And that is using aqueous ammonia in excess. So let's move on to the next question, and probably the last question. Portion of solution from 2BII plus ammonia in what? Drops. We've already been told that copper 2 ion is what? Present. This is ammonia in drops. We expect what? Light blue. If you like, you can just write blue. Light blue gelatinous precipitate. Please always write your precipitate in full. Don't write PPT or don't write precipitate, right? Don't go and spell as precipitate, but precipitate, and don't write it as PPT. So precipitate formed. Light blue gelatinous precipitate formed. We already have the reference there, copper 2 ion. Then in excess, that's excess what? Ammonia. This could only lead to the formation of a complex. When Cu2 plus reacts with excess ammonia, it forms CuNH3 4 2 plus. And this complex, which is responsible for the deep blue solution that is always formed, is called tetraamine copper 2 ion. It is what? Soluble, right? So what will be our observation here? Our observation will be precipitate dissolves, precipitate dissolved to give a deep blue solution. And I told you that that deep blue solution is due to the formation of tetraamine copper 2 ion, and this is always the confirmatory test for copper 2 ion. So our inference here is Cu2 plus confirmed. Cu2 plus confirmed. So that is how the test. So from here now we already know the ions that are present. The positive ion is Cu2 plus and the negative ion is SO3 2 minus. So let's see what we have in the next question. Based on the observations and deductions, state the I, chemical formula of D, II, name of D. When Cu2 plus combines with SO3 2 minus, valencies 2, 2. So when they exchange, they will give us what? Cu2 SO3 2. So these two will cancel out to give us what? Cu SO what? 3. So that's the formula. So that will be what? Cu SO3. That's the formula. It is capital C, small u, capital S, capital O, subscript 3. Not this. This is wrong. Neither is it this. This is wrong. Neither is it this. This is also what? Wrong. Right? So this is the correct formula. And the name of D is what? Copper 2. You name the positive ion first, or positive radical first. Copper 2 trioxosulphate 4. Copper 2 trioxosulphate 4. With that, we come to the end of this tutorial. So if you were able to learn anything from this tutorial, give us a like, subscribe to this channel, and turn on your notification bell if you are yet to do so. Also, don't forget to leave a comment. So until we come your way next time, remember, winners don't quit and quitters don't win. Peace and God bless.